by saying that as we move towards the ensemble, we're going to consider this as a concluding aspect of it. So, and then I started by saying that we started ensemble by looking at this hypothetical case, whereby we considered a kind of 5 different base learners that have been trained on the same data set. And then we can see how a simple majority voting ensemble, this is a simple majority voting ensemble, has been able to convert these very weak learners. Look at this is 57.14 accuracy, 57.14. And then this is 71. Why? By the time we combine these 5, we were able to arrive at 100% accuracy. And I said, this is the power of ensemble that we try to let us understand how it could be taken advantage of. So, and then how does that happen? This is the reality. This is the output of the training of the testing set that we are looking up to. So model 1 is predicting this. Model 2 is predicting this, which is a mistake. So we have 1, 2, 3, 4. There are 3 correct predictions. So which is majority carries the vote. When you get to this place, the correct answer is actually this. 3 models are 3 models correctly predicted this. Whereas only 2 made mistake. So 3/2. So majority still carries the vote. So we get it right. Then again, we have another one here. 1, 2, 3. 3 against 2. Majority carries the vote. So here also we have 2 mistakes and then 3 correctly classified. So majority still carries the vote. So it means at the end of the day, we have all the prediction to be correctly achieved. We compare with the ground truth. So it means the ensemble, the combination of all these various models, even though each of the models as an individual were not really getting excellent result, but their combination resulted in excellent result, which is one of the unique power of ensemble that we can take advantage of at the appropriate time. Now, we have also discussed the concept of the generalized architecture of ensemble, that we need to know what are the possible combinations or options we can have. You have it here, whereby this is a generic model. That's okay. These are possible combination we can have. So now you can have, let's say you have, we have this classifier 1, classifier 2. Now, so here we can have different, let's say we have like 4 classifiers. It could be more than 4. So your combination of features could be the same feature. You might also try different feature spaces. We use feature 1 to 10, feature 12 to 11. You can play with them, it's okay. And also the kind of base classifier you want to build, they can be the same, or the classifier could be from the same model, which we call homogeneous ensemble. That's what you want to use neural network all through, but then you'll be changing the setup of the neural network. The topology is going to be different. That is also fine. And it could be different. It could be different classifier altogether. Different classifier altogether. That is, we use SVM, we use k-nearest neighbor. So we use different classifiers so that we can have more diversity. Because actually one of the ways to get advantage from base learners combination is by making sure that those base learners are as independent as possible, that you can make them. So also on the choice of training the model, so we can have all the training set we can have resampling as we have discussed. So all this led us to the concept of having, we started the simple voting method. We discussed the popular bagging ensemble. And then we also discussed the boosting, which we concluded with the discussion of stacking last week, stacking ensemble. So in the output combination, this is why we talk about combination. We can see there is this kind of, okay, there's room for you to go back again and modify, change things. So this is the advantage of this. You can keep playing with some of the parameters, or how do you set up your ensemble in order to produce either voting ensemble, bagging, or boosting, or stacking, depending on the one you are doing. We also mentioned this concept of fixed stroke train rules. When we are going to combine this classifier, there are two major ways. We have the fixed rule, and then we have the trained rule. The fixed rule is where we assume that, okay, we're going to use voting for it, or we are going to go by the principle of bargaining, majority carries the vote, or we're going to go by voting. If you a classifier that are more accurate, we give it more voting right compared to those one with less accuracy that will give lesser voting right. In which case, if you in boosting, if you have a classifier with 99% accuracy, then we can give, okay, one vote from this classifier is going to be 3. But another classifier with just maybe 75, one vote here is going to be 1 vote. So this is called boosting. We try to boost the performance of those one we trusted. But however, we also discovered that it could also lead to problem, because it means if this model should make any mistake, we are going to be multiplying the mistake also by 3, because we already decided that we're going to have 3 assigned to such model. This is why each of these one mostly they make use of the fixed rule concept. Fixed rule concept. That is, once we select the rule we want to use, they are fixed. That's what you're going to use throughout the setting. However, the stacking took it totally different. That was why we call it a kind of a disruptive technology that took it to a higher level by saying that instead of fixing rule that might have advantage or disadvantage, why don't we try to combine by training another classifier and let that new classifier now train using the output from the different classifier to now make the final prediction. This was the content of our last week discussion, and then examples were given, and we also demonstrated how we can run these stacking from the weaker environment. Now, some of the remarks we have to clarify on the fixed and trained combination strategy, like we just explained. In the fixed combination strategy, so that might lead to any of these, especially this bargaining and boosting. So we say majority vote for bargaining. So majority vote, it means even if your accuracy is 99%, we give you 1 vote. Another classifier with 77% accuracy, we give it also 1 vote, just like we have in some system today. So we don't really care about your experience. We all know the disadvantage of such. However, boosting also came with its own challenges, which is that, okay, we give more vote to those that are more accurate, but then we can also lead to another problem, which is whenever there's a mistake from such classifier, we will be multiplying their mistake also in manifolds, which is also another issue. Now, so we now say that these are examples of fixed rules. The advantage of fixed rule is that they are very simple, simplicity. See, it's very simple. Either either you do it by majority voting, or you assign more weighted voting strategy. Very simple, very straightforward. And it also, it consumes low memory and time requirement. You see? And it is well suited for ensembles of classifier with independent or low correlated error and similar performances. They say this is always good if your base learners are performing in a kind of independent manner or with similar performance. That is, maybe all of them have higher accuracy. We train like 55 models. All of them had like between 95% and 99%. So it means that nearly all of them are performing excellently well. So we can go for majority voting. That's okay, because it's a very simple method. However, for the train rule, the advantage of train rule is flexibility. It's very flexible, which is potentially better performance than the fixed rules. Because in fixed rule, we discussed that if you go for majority voting, you'll be ignoring performance, you'll be ignoring the accuracy of super classifiers. And if you assign more weight to some classifier, you might be indirectly also multiplying their mistake accordingly. However, for the train rule, there's nothing like that. You see, we take the output from the classifiers that are developed as base learners. We use it to train another classifier. This is where the concept of train rule comes in. You see, we use it to train another classifier entirely. So that is why flexibility comes in. It is not fixed. And then train rules are claimed to be more suitable than fixed ones for classifier correlated or exhibiting different performance. They say this is usually good when the base classifiers are having a kind of different performances. Because the idea is that here we are looking up to like we want a situation whereby we have like all the classifier like having like between 95% to 100% accuracy, which might not be possible in some cases, but then if you can have this kind of case, this could be an option. But the good thing about train rule is we don't really care about the performance of those classifiers. In fact, let them be different in their performances. One is getting 45% accuracy. It's okay for us. Because the idea is there might be some very difficult samples that this one is, even though it has low accuracy, but it's actually getting right some things, which even another one that is 95% might not be able to get. So which means we can benefit from the effort of this one, even though it has low performance, there might be few samples where it will be very useful. And that is why, because we are not using the final model, we are not doing voting, tell us what are the maybe probability of getting class A or class B. We're going to use those probability values to train another model. So one way or the other, this one is going to contribute to another training and testing process, which is the advantage of the train rule. See, popular example on the train rule is the one we refer to as stacking ensemble. So it is flexible. Of course, the disadvantage of this train rule, which is the one, if you are facing challenges in your data, I recommend stacking a lot. I've seen students who try to use boosting, try to use stacking, but they couldn't get excellent results. But the moment they use stacking, they try to use bagging and then boosting, but they were not able to improve the accuracy to their desire. But then when they use stacking, they were able to achieve what they wanted. So it has actually proven that it's better performance than stacking and boosting in some cases or in most cases. But we are not generalizing. Like I told you, if somebody tells you in machine learning, this is the best method, that person doesn't understand the concept of machine learning, because this concept I kept reiterating, which is let the data speak. This is very important concept. Always remember, we might have a data set that will only work for voting ensemble. The simplest of them. And you use it on stacking and maybe you get some very weird results. So these are possibilities. So that's why we always encourage people, okay, let the data speak, use different models, try to come up with which one is actually working for this data. So we cannot always generalize that if it works for this data, it must work for that data. No, we have to let the data speak and then see what is going to be the outcome. So the major challenge with the train rule, even though it has the capability of achieving excellent results, in most cases, is that it needs high memory and time requirement. High memory and time requirement. Because it's like you are having double training. We train several models. Instead of just voting to select, we are training another model again. In fact, sometimes you might need to do parameter optimization here, in which case, try to train SVM and see the output. Train another one, KNN. Train another one, maybe decision tree, to see which of them will be able to help you to do the combination in a better way. So we're going to waste a lot of time because it's like double training, double testing at different level of the ensemble development. So it will consume high memory and also time requirement. So you only go towards stacking if really you have exhausted the simple majority voting, then you can then go to all those ones, especially if your data is big, that will need a lot of time to ensure the training. Of course, that is the price you have to pay for getting something that might give you better results. So after you have exhausted those simple ensemble techniques, it is not out of place to try to move towards trying stacking, which is often reported to have gotten better results than others. Now, in some cases, or maybe majority of cases from my own personal experiences, but then we cannot say that it is the best. No, it depends on the data you are modeling. Now, another point we mentioned I want to reiterate here is we say method for fusing multiple classifiers can be classified according to the type of information produced by the individual classifiers. For example, we have the abstract level. We mentioned this last time. Abstract level is when a classifier only outputs a unique label for each input pattern. When you give an input, it tells you that, okay, this belongs to class A or it belongs to class B only. That is the only thing it tells you. The rank level will tell you, okay, class A, class B, this one is, I rank this one as number. If I want to give If I'm asked to select, I'll give one rank 1, rank 2. It means my choices of classes will be, class B is my first choice, class A is my second choice. And if you have multiple classes, it will keep ranking them. Maybe C is the third choice, and class E is the fourth choice, and then D will be the fifth choice, like that. This is called rank level output. And for measurement level output, each classifier output class confidence level for each pattern. So for this one, rather than just giving us ranking of which class I'm going to give, it will say, no, for class A, my probability is 0.8. For B, my probability is 0.2, like that. It gives a kind of confidence. This is how confident I am that A is the correct answer. So we're going to take this value. We're going to take this value to make the final. Now, so we just take these values and then use it to train. This is why at the measurement level, one of the popular ensemble here is stacking. See, at the stacking, for stacking ensemble, we need the measurement level. So you're going to give all this measurement. What is the confidence you have in class A? Okay, it could be probability value or any other value that the classifier is using. So take those values and then use it to train the next classifier that is going to serve as our combining classifier. So now, for each of the above categories, method can be further divided into integration versus selection rules, and then fixed rule and train rules. We already discussed what we mean by fixed rules, where we assume, okay, we're going to use majority voting or weighted majority voting. And the train rule is the example of stacking we have discussed. Then what is integration and selection? What do we mean by integration and selection? Now, see, in the integration system, there are situations whereby we assume competitive classifiers. That is, every classifier has its own advantage to contribute to this union that we are trying to build. Each of them has this. Now, so in the integration function, so sometimes we assume that, or we have a situation whereby each of the base classifier, they are competitive to themselves. So we want to take advantage of everybody. We call it integration. All the classifiers will be involved in the combination that we want to carry out in the assembling system. That is integration function. That is, all classifiers that you have trained like 55. All of them will be used. Irrespective of one is getting this, one is getting 99, we believe that each of them have something to offer because they are we assume that they are competitive on their level, at each individual level. So that if you train as many as you train, each of them, all the classifier will contribute to the final decision. This is the idea. All the classifier will contribute. However, for selection option, you can train as many as possible, train like 1,005 classifiers. You may now sit down and decide to say, okay, out of this 1,005 classifier we have trained, we want to build an ensemble. So what we were saying was that for the selection function, it means you train sets of classifiers as base classifiers that you want to use, or weak classifier as we might choose to call it, but not all of them will be involved in the final voting process or in the final prediction in the ensemble system. So we're going to select some of those base classifiers that we consider to be good. For example, we train like 1,005 classifiers as base classifiers for an assembling system. We now notice some, and we want to use maybe voting. So when we find out some class, we can have a kind of cutoff mark, select those classifiers with accuracy that are 97% and above, greater than or equal to 97%. Any classifier that is having 97% and above, we are going to select it as part of our voting base learners. In that case, we might end up maybe having like 55 out of 1,000 plus. We only got 55 that satisfy that condition. This is called selection-based combination. So during the fusion process, we don't just fuse all of them, but rather we select part of some of them based on what we assume to be. These are those that can contribute to our intended accurate prediction. So this is where the concept of integration and selection comes in when we talk about the ensemble system. So, and sometimes, like I've described earlier, the parallel architecture, the non-parallel architectures and the likes, there are a lot of possibilities that could be explored. Now, example in this, for the majority voting rule, we have the fixed rule at the abstract level. See, the majority voting rule, if you use the fixed rule at the abstract level, because the AI is going to just output for us, this is my class. And then we take the output of each of them, and then we can vote based on that. So fixed rule at the abstract level, we'll go for majority voting, it could be bargain, and also of others. Whereas for the train rule, we're going to have train rule at the measurement level, actually. You see, measurement level, we don't want to be training another, we don't want to train another classifier with just A, B, this is my output. No, rather we want the measurement. What is the confidence you have in each of the classes? It could be in form of probability values. So we take those values, 0.8, 0.2, 0.3, 0.7 from each of the classifier, and we use it as a new set of features that we're going to use to train the combining classifier. That's going to help us to now merge together the output from each of the classifier, as we have explained in our video last week. Now we now pass a small analogy between designing a single model and designing an ensemble model. Here's an analogy. See, when you are designing a single classifier, analogy between multi-classifier design and single classifier design. When you have multi-classifier design, we are talking of ensemble. Pay attention to that. We are talking of ensemble. So in the multi-classifier, in the single classifier design, we talk of feature design. We think, okay, what are the features we want to use? How are we going to get the features? Then you design the classifier. The next one is to look at the performance evaluation. See, after you build the model, test the model, then check the performance evaluation of the model. This is for single classifier. See, this is for single classifier building block. However, for ensemble, we have to think of the ensemble design. You see, which kind of ensemble do you want to build? How do you want to build the base classifiers? Am I going to use resampling with replacement, or I'm going to use different feature spaces? This is what we have to design at this level. Then after that, we look at the diffuser designer. Are we going to use the train rule, or we're going to use the fixed rule? Majority voting, weighted voting, and others. And after that, then we check the performance measure and then see which of them is giving us better result. So now we look at a brief review of all the ensemble types we already looked into. See, this ensemble type. This is the classifier type we are using, the sampling used, and then the training strategy. Now, look at the ensemble method. For the basic voting one, we use different type of classifiers there. That is heterogeneous, because we are using the same training set. Complete training sets are used for training all the classifier. So preferably you have different classifier because you are using the same training set to train different classifier. That's why this is good to be heterogeneous ensemble, heterogeneous. And then training strategy is that it is training parallel. They are in parallel. So you can, individual people can train it and then they can come and combine their results. For the bargain, we have different or same types. Anyone goes here, you can have different type of classifier, and you can also have the same type of classifier. Then we have the random sample with replacements, which we call the bootstrap sampling that is used. So to generate different sets. So you are not using the same training set, and that is why you can have the same type of classifier. And if you are having the same type of classifier, you cannot train with the same training set like this. Otherwise, it's going to have, it has no meaning, because you'll be generating the same model for all what you are doing. But then with random sampling with replacement, then you can be generating different bootstrap sampling for training each. And then it is also training parallel. So any ensemble training parallel has the advantage that it is less time consuming. It's not going to consume a lot of time. For the boosting, typically of same type, So it's typically of the same time. However, like I mentioned, someone might want to explore the possibility of using different types, but then it's going to be more complicated because here it is trained sequentially. You have to train one, look at the output coming from that first one, see those samples that are being mistakenly classified. It is those samples that you have to focus more in the next classifier. And that is why boosting will make a very weak learner to become very strong, because you keep exposing that classifier into those that it cannot classify in the previous stage. So at the point in time, it will understand all the data samples appropriately. So this is why typically it is using the same classifier. But however, using different one is not an impossibility. As for sampling method, it is using random sample with replacement, and it is sequential, and it's one of the one that will take time, because you have to finish one before the other. You have to finish another training. You want to train base learners up to like 55. So you have to train one, finish before you analyze it, and then proceed to the other one. You can imagine how long it's going to take in this kind of a system. And the last but not the least is the stacking. In the stacking, you can have different or same type, very flexible one. So sampling can be, you can use the complete training data set. That is, if you are using different classifiers, then it's okay to use complete training set for them. Or if you like, you can also use different random sampling types. So stacking is very flexible, and this is one of the advantages of this method from my own personal experience. It's very flexible with you. You can try out several options. Now, so stacking can have different same type, complete training, or different random sampling. And also, now, for the base learner training strategy, it is parallel. As you know, you can do it in parallel. Special cases of sequential could be explored. You see, there are situations whereby you can have a kind of an hybrid system. The concept of boosting could be used as part of the base learner development. So if in very serious cases, when we are stuck, we want to get excellent result, but we are not able to get it, we can bring in some boosting as part of the base learners. So try to make boosting as part of the training learner. In that case, this is why we say that special cases of sequential could be explored, but ideally it is usually in parallel. You train several classifiers in parallel, bring us the output, then we use the output to train another classifier that's going to combine for us. However, we can explore special cases, especially when we have data set that is not cooperating and we're having difficulty in getting the best result that we envisaged. Now, looking at the pros and cons, the advantages and disadvantages of Ensemble, as you know, there's nothing with advantage without its own shortcomings. So, however, you have to weigh the two. Which one is better for you? Advantage is better than the other one, then you decide. Now let's look at it. First, we say that Ensemble is a proving method for improving the accuracy of the model and works in most of the cases. This is an established case. Ensemble is a proving method for improving the accuracy of the model. Most cases, Ensemble will perform better than individual model. That is what has been noticed. Ensemble makes the model more robust and stable, thereby ensuring decent performance on the test cases in most scenarios. So once you build an Ensemble, for example, you can build an individual classifier. It might be performing on a test set, but when another test set comes from the company or from the client, it may not be able to recognize it. However, when you build an Ensemble, because it's going to take advantage of several classifiers, as we have explained, so you can see that the possibility of always getting excellent result is very higher when you are using Ensemble compared to when you are using individual classifier. We also say that you can use Ensemble to capture linear and simple as well as non-linear complex relationships in data. See, which we can do by using two or different models or more models to form the Ensemble. It's usually advisable that when you are forming your Ensemble, try to use different classifiers so that the Ensemble can take advantage of different background, different learning principle of each of the classifier diversity that you're trying to explore. It's not out of place to use the same classifier as we have explained. However, it is preferable based on experiences that have been shared in different research works that when you combine Ensemble with using different classifier, you are likely going to take a very big advantage of the diversity that is involved. And of course, the cons, the disadvantages. So Ensemble reduces the model interpretability, see, and makes it very difficult to draw any crucial business insight at the end. So at the end, this is the challenge of Ensemble. You can also see that we have been mixing different things together. You know, when you keep mixing things together, at a point, it gets very, very difficult for you to really say, where is this one coming from? Where is this one coming from? So that is why a very big disadvantage of Ensemble is that the interpretability of the model is sacrificed for accuracy. So, and then we have situation whereby really accuracy is what they want. How do we get the accuracy? Some areas don't really want it, they don't care. However, if it is an area where they care more about the interpretation of the result, especially when it comes to business insight and decision making, then you have to carry your client along. Perhaps Ensemble might not be a good option for you to use in that kind of scenario. You might have to look for individual models that could achieve their acceptable accuracy. I have seen people that will tell you that with just 80% accuracy for my own business idea, it is enough for me. So in that case, why are you wasting your time developing Ensemble that can get 99% accuracy when the client will also criticize you that we don't care about all this accuracy you're talking about. We care about the business insight. And your model cannot provide insight for us because you said Ensemble reduces the model interpretability. So what I'm saying in essence, you need to sit down your client, look at what do they really want. As we know in life, you cannot eat your cake and have it. Sometimes you have to make sacrifice. So you either sacrifice some little accuracy. Okay, 85% is okay for me. With decision tree, anybody can easily understand what you have built. They can make it's very interpretable. The crucial business decision can be easily made and inside affirmed. However, if you are in a medical area whereby they are really more crucial that we want to predict if somebody is going to die from this surgery, we just need the accuracy. So we need the accuracy. The data set is there. Then you go to any level, bring in as many stack several Ensemble. You can even do hybrid of Ensemble. You have bagging, you have boosting, then you use stacking again after them and try to get the best possible accuracy you can get. So, however, if interpreting result is your client's main objective, then Ensemble might not be an option for you. So we have to know what to sacrifice and for what. We also say that Ensemble is time consuming. Therefore, might not be the best idea for real-time application. If you have real-time application whereby input need to be taken and answer provided immediately, do this, don't do this. Like beam packing in an online assembly plant. We want to be sorting some product that is being produced. We want it to be decided immediately. Then perhaps you have to think about the Ensemble you are developing. If it's going to be time consuming, then maybe you have to think of another simple model to use. So then the selection of model for creating an Ensemble is a very challenging thing. So which one should I use? Should I use k-nearest neighbor? You have to try and error. It's one of the challenges AI in this field. You have to do different method. Because of what? Because of what I always say, let the data speak. So you cannot really tell which of the algorithm will produce the better Ensemble for you until you have tried them out. No matter the professional advices people give to you, you always need to try out and see which of them will work for you. Because theory apart, when we get to the field, we let the data speak. That is a principle that cannot be taken away from machine learning in the foreseen future. And finally, concluding, we said that bagging is to decrease the model variance, while boosting try to decrease the model bias. So stacking try to increase the predictive force of the classifier. That is the essence of stacking. So therefore, using techniques like bagging, boosting, and stacking help us to decrease the variance, bias, accuracy, respectively, and increase the robustness of the model. Robustness in the sense that the system will always guarantee that you're going to get good results. This is the advantage of an Ensemble, robustness. You see, there could be a classifier getting 99% accuracy or even 100% accuracy, but being an individual classifier, you cannot guarantee that it's going to always work when new data sets is coming in. So in this case, Ensemble might always guarantee you that, okay, bring any data set, the ensemble, because they have different models working together to produce the better result. This is just like a team. When you have a team working, you can always guarantee that your job will be done as at when needed. Unlike when you depend on a single individual who could fall sick anytime, anything could happen to him, he could make a mistake. So that is even in real life. You can rely more on a team than rely on an individual, because anything could happen to an individual. But for a team, at least if few of them are available, the war will continue to go. And that is essentially what Ensemble is bringing to the table. Finally, we say combination of multiple classifier decrease variance, especially in the case of unstable classifiers. In the classifier, we classify as unstable. They may produce more reliable classification than a single classifier, as we have demonstrated when we describe some of the methods earlier. Therefore, the expected performance of the ensemble is guaranteed to be no worse than the average of the individual classifiers. So it has been proven that, so if you spend some time to build ensemble, the good news is that your ensemble will always guarantee that it will not get less than the average of individual classifiers. So that is why somebody say, okay, if you build an ensemble, you really have nothing to lose, because it will only guarantee that you have at least minimum of average of individual ensemble. But in most cases, it gets even better result than what individual can always provide. So this is going to be our concluding part of this work on ensemble. And finally, we remind ourselves about the generic framework that we discussed earlier. So which is, where do we integrate ensemble to? This is the framework we have discussed earlier. See, you start here. This is a small flow chart. You start gathering your data, see, and then preparing your data. Then you do data preprocessing. Maybe you need to clean your data. You need to do normalization of data. You need to try to track down missing values and treat missing value, treat outliers. So many other things you need to treat. We've discussed in some of our previous videos. Now we move to model building. This is where you need to start by building simple model. Start from very simple one. This is my friend, K-nearest neighbor. Tell me your friend, I'll tell you the kind of person you are. If I know your neighbor, I can be able to predict if you're a good person or not. Start from simple model, then build the model, test the model, check this. Is it okay? There's need to refine the model? Yes, I need to refine the model. Change the parameters, turn the parameter, go back again. Turn the parameter. So how do we turn the parameter? This is an area, inshallah, we're going to look forward to. We're going to make videos for us on this, how we can play with a parameter, how we can make a parameter become better. So keep doing that. Sometimes after turning KNN parameter for so long, we are able to get only just maybe 85% accuracy. We have tried all what we can try. Okay, try another one. Try SVM. We try SVM. We have tried decision tree. We tried some of the method we knew. We are not yet okay. Maybe it is time for you to go to Ensemble. See? So the same principle, you are going to use it again. Okay, try basic voting. Bring the result of all these guys you have been working on. Can you combine them in an ensemble, madam? A voting ensemble, bargain or boosting, or go to stacking level. So this is the same area. We call it learning from data. This is the middle phase. This is phase 2. Phase 1 is data preparation. Phase 2 is learning from data. This is where ensemble also comes in. But then my advice is always try to check on simple learners, simple classifier before going to ensemble. If all things goes on well after simple learners have been used or ensemble has been deployed, then you do model validation. You have another reserve data or a new data coming from the clients, from the industry, and then use it to check if the model now, because you are building model using the parameter obtained now. This is the final model. Now use data, other data to check it if it's okay, validate the model. Now predict real life using this particular model, analyze your result, interpret your result, identification of hotspots, and this and others are going to be part of what we are going to start discussing hopefully next week, when we hope to start discussing on how can we practically utilize all what we've learned so far. in our day-to-day activity, especially as researchers. So how can we use them? So we try to take it now to real life implementation. How do we develop a research work from machine learning point of view? What do we look into? What do we focus on? And so many other questions that we're going to be looking at. The grace of God is going to be our focus starting next week. So thank you all, and then I wish you all the best. Thank you.